All right, Bob, we'll be getting started soon. Getting Trevor to get you on the screen. And you are there. Can you test out the audio to see if you're
Yeah, I'm testing. Am I
not yet. I think Trevor's still working on making sure that's it. Right, Bob.
Okay, testing. Versatile computing on Expanse. Is my video, sorry, is my audio okay? Testing. Is my audio okay? Okay, Cindy, we're all ready to get started. All right, so good afternoon, everybody. My name is Bob Sienkiewicz. I'm the Director of Education and Training at the San Diego Supercomputer Center. And today I'll be talking about versatile computing on Expanse, focusing on research being done in the physical sciences and engineering. So before I get started, I just do want to mention that Expanse is supported through an award from the National Science Foundation. So before I get into the science, I'm just going to give a little bit of background on Expanse. I think some of you may be familiar already, but I'll just bring everybody up to speed. So the theme of Expanse is computing without boundaries, cyber infrastructure for the long tail of science. And what we mean by that is that Expanse was designed to support the requirements of users and researchers with kind of small to medium-sized computing requirements. And by medium, that could still be fairly large. We have a cap of about 4,000 CPU cores on any individual job, but that really covers most of computational science requirements. So, Expanse was built in response to an NSF solicitation. We are what they call a Category 1 system, which means we're a capacity system. So from day one, we're really going into full production, as opposed to the Category 2 systems, which are more experimental machines. Our program officer at NSF is Bob Chaddock. The PIs for the project, most of whom are here in Dallas, are Mike Norman, Ilkay Altintash, Amit Majumdar, Mahidar Tataneni, and Sean Strandy. The system was funded with $10 million for the acquisition, and then another $2.5 million per year for operations and maintenance. The primary vendors are Dell for the HPC system and Eon Computing for the storage. And then the compute, the interconnect, and the NVMe were provided by AMD, Intel, NVIDIA, and Mellanox. So a little bit more background on Expanse. As I said, we are computing without boundaries. It is both an HPC and a data-centric resource, peak performance of about 5 petaflops. On the HPC side, Expanse is built from 13 scalable compute units, and I'll describe what these scalable units are on the next slide. As a total of 728 standard compute nodes, 52 GPU nodes, with a total of 208 GPUs and a small number of large memory nodes. On the data-centric side, we're backed up with 12 petabytes of performance storage. These are Lustre parallel file systems with a peak bandwidth of 140 gigabytes per second and 200,000 IOPS. We have fast local NVMe storage on each compute node We're also going to be deploying 7 petabytes of Ceph object storage, and we are connected to high performance research and engineering networks. In the long tail of science, we are really focusing on many different domains of science. These include multi-messenger astronomy, genomics, earth science, social sciences, and we also have a number of innovative features such as composable systems, high throughput computing, science gateways, interactive computing, containerized computing, and cloud bursting. So a little bit more about the Expanse architecture. I'm not going to go into too much detail here, except to emphasize that Expanse is really designed for high performance, for reliability, for flexibility, and productivity. I mentioned in the previous slide these scalable compute units. So what we've done is in each rack, we have 56 CPU nodes, each with AMD EPYC processors, and also 4 GPU nodes. In each of these scalable units, we have a lot of compute power, but what's nice about this design is it allows us to expand Expanse as needed. So for example, last year we had added a additional rack or additional scalable unit to support our industry users. A little bit of overview of how Expanse is being used. So I should point out that only a fraction of the research being done on Expanse is NSF funded. Some of it is non-funded. Some of it has funding from other sources such as NIH, Department of Energy, Department of USDA, and foundation support. But when users ask for allocations on Expanse, previously through the Exceed program and now through Access, we ask them to let us know, which field of science it falls into, and this is using the NSF categories. And we find on the CPU side that it's the mathematical and physical sciences, geosciences, and engineering that really dominate the usage, where on the GPU side, the biological sciences are dominating. And if you were here for my talk yesterday, I went into that a little bit with the biological sciences, where there's a handful of real killer apps, such as molecular dynamics and phylogenetic tree construction, that are really driving that usage. So with that, I'm going to go into some examples of the science that's been accomplished with Expanse. I'm going to start off with the few use cases from astronomy and astrophysics, beginning with work by David Nielsen at Brigham Young University and his collaborators at the University of Utah. So they're studying gravitational waves that are generated from binary black holes, binary black hole mergers, where the black holes have large mass ratios. And these simulations will hopefully improve the methods for detecting gravitational waves using existing observatories such as LIGO and LISA. So what we see here on the left is visualization of a black hole binary, in this case with the mass ratio of 4:1. And then the surfaces, or the isosurfaces, are showing gravitational wave extraction from the simulation. Below that, you see a plot showing the signal that we expect from a gravitational waveform from a 16:1 black hole binary merger. On the right, you see an example of a 2D slice of a 3D simulation illustrating the adaptive mesh refinement. So you'll notice in the vicinity of the black holes that we have a much finer mesh. As we get further away from the black holes, we have a coarser mesh. And what this allows us to do is capture the physics at full resolution in the areas of interest, but without having to have such a fine grid in the areas that we're not as interested in, where there's not as much physics involved. So this could make the calculations much more efficient. Okay, another astrophysical application. This is looking at the merger of neutron stars. So what's really, I think, novel about this work being done by David Radice and his colleagues at Penn State University is that they are predicting that at the very core of this neutron star merger, that the densities of matter are becoming so high that the neutrons and protons are actually disintegrating into what we call a quark-gluon plasma. This is a very, very exotic state of matter, only found at very high pressures, very high temperatures. In the universe, this was the state of matter at the very, very earliest fractions of a second after the Big Bang. What I like about this work is that it also has a tie into experimental observation. So David and his group have predicted the way of the gravitational waveforms that we would get with and without this phase transition to a quark-gluon plasma. These waveforms are very different, and hopefully LIGO and next generations of detectors should be able to distinguish these signals for nearby mergers and really determine whether or not this quark-gluon plasma formation is occurring. Continuing in astrophysics, this was work done by Peter Adsheed at University of Illinois and Zach Wiener at University of Washington. So they were doing large-scale numerical simulations of the universe, looking for the origin of dark matter. And not only that, trying to predict the resulting spectrum of the gravitational waves in the background that would provide a signal for this mechanism. This is one of the groups that was making extensive use of expansive multi-GPU capabilities. A lot of the GPU work that's being done is really single GPU or very loosely coupled calculation. This was a case where they needed to take advantage of the fast communications between the GPUs. What you're seeing on the left is a few 2D slices from a 3D simulation of the density contrast. So this is at 3 different times. You can see the evolution of the system. And this is another case where the computations really have strong ties to the experimental work. So on the right, what we're showing three different plots for the spectrum and the gravitational waves generated using different model parameters. And then in kind of the top half of that figure, shaded in the light blue color, is the area that the future laser interferometer space antenna should be able to probe. And as you can see, these 3 different models predict very, very different spectra. So this combination between, combination between computation and observation will help us to determine which of the models for dark matter formation is actually correct. One more astrophysical application. That this is simulating the generation of jets from binary neutron star mergers or neutron star black hole mergers. These energetic jets are observable, throughout the universe. They also tie into modeling of gravitational waves. So what we're seeing here is 3 different simulations showing the remnant of a black hole. But a black hole binary merger and the associated jets for 3 very different models. Okay, switching to high energy physics, this is work in lattice quantum electrodynamics being done by John Kogut at University of Maryland and Donald Sinclair at Argonne National Lab. So Kogut and Sinclair are really giants in the field of lattice quantum chromodynamics. This is what we use to study the properties of quarks, of nuclei, basically any hadronic matter, anything that interacts with a strong force. But they're also beginning to apply these techniques to quantum electrodynamics. And this is going to be important at the very, very high electric or magnetic fields that we're going to see in future generations of intense laser facilities and electron-positron colliders. Now, where the latter is so important is that the current version of particle colliders, like the Large Hadron Collider, primarily involve collisions with protons or antiprotons. Now, these are very, very messy collisions. There's a lot of structure within a proton. You have quarks, you have gluons, and it makes it very, very hard to interpret the results of these collisions. These electron-positron colliders are going to produce much, much cleaner results. But we do need a deeper understanding of what's going on at these high energies. So I'm next going to cover a couple of examples of solar physics that were studied using expanse. So the first was work done by Predictive Sciences, Inc. They had used expanse to perform MHD, magnetohydrodynamic simulations of the sun's corona. And they did this in advance of the December 14th, 2020 solar eclipse. And this was one that was visible in Chile and Argentina. So these models give us a lot of insight into how the corona is heated and how supersonic solar wind is accelerated in the interplanetary space. Now, why this work is important is that these solar winds can have a big effect on communications and even power grids on Earth. So a better understanding of the formation of these solar winds will help us better respond to large-scale solar storms. Other work being done in solar physics, this was led by Alfred Mallet and his lab at University of California, Berkeley. And they've been doing simulations of the magnetized turbulence in the sun's corona. This was a different type of calculation. They were doing something called direct numerical simulation. This is a fluid dynamics technique where we resolve the very finest motion of the fluid elements, in this case, not using an approximation to model the turbulence. And by doing these very high accuracy DNS simulations, they were able to uncover some striking phenomena. They could see that the turbulent fluctuations were coalescing into large stable structures known as alpha vortices. Now, these had been observed before in the solar wind, but until this work, the origin of these vortices has really been a puzzle. So this foundational work, really helped to interpret some experimental observations. Switching to climate simulation, this is work being done by Mike Pritchard and his team at UC Irvine. So they were using the GPUs on Expanse to train variational autoencoders. And this allows them to do a very high resolution analysis of climate simulation data. So these are the kind of calculations that have just been overwhelming using more conventional statistical approaches. And by doing this, they are able to analyze larger data sets, do this quicker, and do a lot of numerical experiments. Like what you're seeing on the right is, for example, what would happen if we had 4 degrees Kelvin of warming and the effect that would have on global climate. Okay, I'm going to switch and talk about a few applications in chemistry and material science. So this is work being done by Jingyun Yi at Clarkson University, and he's been using Expanse to study the structure of metal organic framework supported copper nanoparticle catalysts. Sorry, that's a bit of a mouthful. And these are important for certain industrial chemical processes, such as the hydrogenation of carbon dioxide to form methanol. Methanol is one of the feedstocks that's further used in many chemical processes. Switching to some other work that's being done in catalysis. This is being led by a team at University of South Carolina in lab of Andreas Hayden. He's been doing a combination of Bayesian statistics, DFT, and experimental studies to identify active sites for propane dehydrogenation on various platinum surfaces. And from this work, he was able to identify that what's called the 2-1-1 surface of platinum. So don't have time to go into the notation, but you could think of these notations 100 or 211 referring to different slices of platinum exposed in different surfaces. And this work showed that the 211 surface platinum is the relevant active site for the dehydrogenation of propane. Also in the area of material science, I'm showing here work being done by Liming Zhang at Iowa State. They're interested in the design of amorphous crystalline metallic composites. This work has a lot of practical applications. These composites will have mechanical and thermal properties that can greatly exceed those of existing materials. Lots of applications, say in aerospace design, where we need very high strength, tough materials, also at lower weight. More work being done in material science is being carried out by Beth Nowadink's lab at UC Merced. So she's using expanse to perform DFT calculations on layered perovskites. But what's interesting about this work is that these are lead-free material. So if you've been following the literature on photovoltaics, currently most of the photovoltaic materials are based on silicon. These perovskites have the promise to be both inexpensive and highly efficient. But one of the problems with perovskite materials is that most of them are lead-based. So developing these lead-free perovskites could give us more environmentally friendly solar panel materials. This is work being done by Peter Schultz at Arizona State University. He's using expanse to do multi-scale simulations of the self-assembly of DNA nanoparticles. So by multi-scale, we mean everything from finite element simulations down to all atom molecular dynamics. So these nanostructures can then be used as a scaffold for constructing very complex optical metamaterials. Again, one more example in the area of material science, that this is being done at Johns Hopkins University. So they're interested in the formation of microstructures during selective laser melting. So this is an additive manufacturing technique, which can also lead to stronger, tougher, lighter, more thermally resistant materials for aerospace and other applications. And then just a few more examples. This is work being done by Jacek Yakowski at Oak Ridge National Lab. He's using techniques called time-dependent density functional theory and real-time TDD-FT to investigate the properties of silver nanowires. This is work that's highly relevant to the development of temperature and pressure sensors, including wearable sensors. And just a couple more examples. This is work being done by Chris Vandewal's lab at UC Santa Barbara. So he's interested in the properties of what we call ultra-wide bandgap semiconductor materials. And these have a number of applications. So they could be used in high-power electronics. They could be used in extreme environments, say in space applications, and also in materials for quantum information and quantum computing. And then finishing up with one more example. This is work being done by Elizabeth Hicks at Epsilon Delta Labs. She's using expanse to do reactive computational flow dynamics simulations. By reactive flow, we essentially mean combustion, using something called the NEC 5000 spectral element code. So this work is still in a pretty early stage. She was really interested in performance for now, rather than investigating new physics. But she found that expanse performs similarly to Comet, our previous supercomputer, for smaller jobs, say those that fit onto 1 or 2 nodes, but that she's getting much better and much more consistent performance than Comet as she scales to larger jobs. So with that, I'm just about ready to wrap things up. I'm going to say expanse has had a tremendous impact on research and engineering, the physical sciences, and we've seen this in many different areas. In the development of new materials in high energy physics and climate, astrophysics and catalysis. The feedback on expanse has been overwhelmingly positive, particularly with regards to application performance and ease of use. And actually I have one or two more slides before I'm ready to take some questions. First, I do want to wrap up and thank everybody who made Expanse such a success. You know, our collaborators, our partners, the users, and the team at SDSC. Showing the names of the folks who were instrumental in launching and maintaining Expanse over there on the left. A reminder, Expanse was made possible through a grant from the National Science Foundation. And if you have a chance, please go out and visit the vendors who contributed to building Expanse. And then finally, I'm just going to make a pitch for a conference that's going on next year. PERC 23 is going to be held in Portland, Oregon on July 23rd through 27th. The call for participation is now open. If you're unfamiliar with PERC 23, we really focus on the research computing community. We have tutorials, workshops, and tracks on applications, systems and hardware, and education workforce development. And with that, I would be happy to take any questions.
Thank you for that. We've got a few people around here. Does anybody have questions? Any questions, Amit? All right, Bob, we're going to thank you for coming in live from San Diego.
Great. Thank you, Susan. Thank you, everybody, for your attention.
All right. Thanks for joining us. We'll see you back at home.